Hey everybody. Thank you all for coming in today to the first People Who Love meetup of the year and the third one of all time. Thanks for coming even though it's like negative 28 outside. Today we have Dan Toliver talking about fast functional list. Enjoy.
Thank you. Thanks to David and James for setting this up. I'm so happy that we have a Papers We Love meetup here in Toronto. That makes me very pleased. Did you guys all have a good holiday?
Woo.
I've got markers that come in red and green, so we're going to be continuing the holiday spirit today on the whiteboard. Very festive. So, how many people read the paper? 4? 3.5? Oh man. I was actually hoping no one had read it, then I could make up anything I wanted. Audio's good?
I think so.
Okay. How many of you have used a linked list before? Wow, almost everyone. Half of this talk is introduction to linked lists. So we're going to cut down the running time a little bit. That's good. How many of you have implemented a linked list before? And almost half of you again. Goodness gracious, you guys are ahead of the curve. If only you had read the paper, then my job would be really easy right now. Cool. So before we talk about the paper itself, let's talk a little bit about the guy who wrote it. This is Phil Bagwell. He passed away, sadly, a couple years ago. He started off as an engineer and then spent 30 years in marketing. And that is a little odd for someone that we're going to be reading a paper from today. It's really hard to find images of him online, but through my exhaustive scientific research, I've discovered that if you do find images, he is always wearing that pink shirt. Every single image you can find and talk that he gives, it's in that pink shirt. I'm not sure why. Yeah, he was by all accounts an all-around great guy. But how did he end up writing papers if he came from marketing? So the story of this paper is kind of interesting, actually. One day, Phil wanders into Martin Odersky's office. Odersky is the father of Scala, among other things. They've never met before, and Phil Bagwell says, "Hey, I've got these ideas for a data structure, and I'd like to write them up and into like an academic conference paper and present it, but I'm worried that the conference committee is going to steal my ideas. What do I do?" And so Odersky says, "Well, you know, conference committees don't usually steal the ideas that people submit to these academic conferences, but if you're really concerned about this, you can publish a tech report in EPFL at our university. We'll just publish a tech report for you, and then you've got prior art on this, you've got precedence." So they end up talking, and Odersky eventually says, "You know, these ideas are pretty interesting. Could we maybe adopt them for use in functional programming languages?" So they think about it for a little while, and it turns out that you can. So the paper that we're reading today, the one that is linked to, is the tech report that was published. And those of you who read it probably saw that it's pretty rough, right? This is kind of a pretty raw form in some sense. There's a cleaned up version, but it's only available as part of the conference proceedings that it was eventually submitted to. And those aren't really available online unless you scour some Russian servers or something. Otherwise it's, I don't know, $80 or something to buy the conference proceedings. But this kind of rough, scrappy paper from someone completely outside of academia ended up being, in some ways, the basis of the data structures that are very commonly used in very common functional programming languages today. So closures data structures, its fundamental data structures, all stem from this, and we'll see later in the talk kind of that evolution of how they went from here to there. And Bagwell continued to be part of that evolution through the entire time, publishing papers through all of the 2000s up until he passed away. with Odersky and with T.R. Gromph and other people on data structures that continue to push the boundaries of what we can do quickly and efficiently, and in particular what we can do quickly and efficiently in functional programming languages. So I think this is a really exciting story. Not many of us here come from a academic computer science background, at least not in the sense of being postdocs that are publishing papers. So I think it's very inspirational in some ways that someone who is willing to put in the huge amount of time and effort to become a world-class expert on the subject can make a substantial difference in this field of computer science research and also in practical functional programming languages. That's amazing. Of course, it helps if you can walk into Odersky's office and get his help to do that, but I think this is a pretty inspirational story in some ways. So let's talk about linked lists, which you are all already experts on. So I'll see if I can draw right-handed while maintaining the microphone left-handed. I suspect this is going to be trickier than I'd hoped. -1 defeats of dexterity. All right. So a linked list looks something like this. We've got some data, let's say 2, and then we want something else in front of this data. So we want to add another item to this. So we're going to add something like this, and maybe we want another item. So we're going to add something like this. All right. So here's a linked list. Almost everyone raised their hand when I asked if you were familiar with this. Okay. Almost everyone is nodding their heads. I hate skipping things, but I think I have to slightly adapt the talk to the current audience. So if you are unfamiliar with this, then I apologize because we're going to move quickly. Okay. So what are the advantages of a linked list? Yell them out at me. What are some nice things about it?
Constant prepending?
Yeah. So let's call that cons, or maybe push if you're more comfortable with that. So we've got constant time prepending, constant time cons or push. You had one?
There's no wasted space.
There is a constant amount of wasted space.
Yeah.
Right. So our wasted space is constant, is linear really. It's actually not constant wasted space. It's proportional to the number of cells that we have, right? Because every one of these contains a pointer. Actually, let's have both a pro side and a con side. And we're going to put that on the con side because we'd like to do better, right? So we have linear wasted space. This is going to be impossible to read, I'm sorry. And that's a cons of our cons list. Yeah. Right, so what are some other advantages?
Insertion in the middle in constant time. No wasted space.
Insertion in the middle in linear time.
Linear is always really good.
No, if you know, okay, if you know where you're going to insert it, if you don't have to find where it's constant.
Given a pointer to where you want to insert.
Yes. Like you can.
Yes.
If I were to insert my 1 in the middle.
Yes, let's rephrase that slightly.
Yes.
So one thing that we can do is always keep adding on to the beginning of this, right? That's our constant time push, or cons. Another thing that we can do is we can constant time, so one, let's call this pop. And the way we do that is just by following a pointer back 1 level. I should probably spell this out a little more clearly. Okay. So
To clarify, is this an immutable linked list that we're talking about, or a mutable?
that's an excellent question.
Okay.
Yeah. So the properties that we have under our pros and our cons are going to depend heavily on how we behave with this, right? If we agree not to mutate things, then we get persistence. If we decide to mutate things, then we lose persistence, but we gain potentially the ability to how do I say this without saying mutate things, because I'm trying to define. So we gain the ability to make an edit in here of various types. And usually those are still going to be linear time edits because we have to get to it. And even with mutation, our seek time is quite bad, right? Okay, so I've just said a bunch of stuff and given you a bunch of pros and cons, so let's write some of these down, okay? All right, so, do you want me to do this, or? Yes. Okay. Cons of cons is wasted space. So in this version, 50% of our space is wasted. And if we want random access read or direct access read, that's going to be linear time in the size of the list. So if you have a big list, and you're accessing into it quite frequently, most of that's going to be happening at constant time, which is going to turn any operations that should be constant time if this was linear into O(n) squared time, which is quite bad. You really don't want that, right? So you want to use a linked list if you're doing a lot of operations up here at the business end, because we can push onto it and we can pop off of it in constant time. And the popping behavior that I still haven't described is following. So if we have a pointer to this head that contains 0 and a pointer, this is a console, it contains 2 things. We can follow this pointer to the next part of the list and consider this a popping operation. So we've updated our pointer and it's now pointing to 1, 2 instead of 0, 1, 2. Is everyone on board with this? Okay. So O(n) pop, and what else do we need up here? We need persistence if we're treating it immutably. So persistence means if I've got a pointer here and I've got a pointer here, no changes that I make to this part of the list are going to affect my pointer here. That's a really bad way of describing persistence. Okay, so if we've got a data structure, a linked list A, and another linked list B, changes to A won't affect B, even if they share some structure and state. Does that work for you? Okay. And if A and B share some structure, or are in fact the same list, and a change to B can be seen by looking at A, if we can observe that change, then we don't have persistence, and we do have mutation. Okay? So this is a trade-off that we have to make, but because we're talking about fast functional lists, we're going to want persistence, and we're not going to want mutation. Everybody good? Okay. There's a couple other important pros and cons. Linked lists are easy to allocate because we're always just allocating little tiny blocks of size 2, whatever that means in your particular system. Okay. They are simple to implement and they are easy to garbage collect, but fairly time expensive to garbage collect because we do have to walk the entire list marking everything in it. Does that make sense? Okay, lots of nodding. Good. All right, so easy garbage collection, but expensive. And simple. They're easy to implement. And they're recursive in a particular way that we like for functional purposes. Okay, Everybody on board with that? So the question of this paper is how do we take linked lists and get all of their advantages? So we have constant time list operators of push pop. So list operators are going to be cons, car, and cooter, which are equivalently, quote unquote, equivalently push, pop, and we'll call this peak. Okay, so we want these to be constant time. This is important for our purposes when we're using lists, but we would also like to get constant time random access and constant wasted space rather than linear wasted space. That would be lovely. And yes?
Sorry, just as far as the constant wasted space, I don't understand how you can have.
How you can have constant wasted space. What does that even mean?
Well, yeah, because you have if you have n elements in a list, you can't have less than n amounts of space taken up.
Yes,
Right.
correct.
So it's but that's a linear amount of space.
The space taken will always be linear.
Okay.
What we're interested in is the wasted space, yes. So we would like the wasted space to be fixed as opposed to proportional to the amount of data that we have in there. And in a linked list, in this form, our wasted space is proportional to the amount of data that's in there. Because for every data item, we also have a pointer. If we're storing, for example, single bits here, which would be a terrible idea, but if we were, and we're on a machine that has 64-bit pointers, then our ratio of used space, of valuable space to wasted space is 64 to 1. That's really bad. Like, we're wasting almost 2 orders of magnitude of our space. So we'd like to do better than that. There are some other cons here too that he mentions in the paper. So another one is that we have really bad data locality potentially. In other words, when we go to load this into a processor, these cells can be spread out anywhere in memory. So a fundamental problem with doing what we're going to try to do today is that memory is essentially just a big linear contiguous blob. And we need to take some parts of that up for our data. But we don't always have access to all of it because some of it might be claimed by other things, right? So when we're allocating cells for a linked list, this is really easy because we're always looking for really small pieces, but those small pieces might end up fractured across memory. Does that make sense? So then when we go to load, the first n items of the list, we're loading from here, we're loading from here, we're loading from here, we're loading from here. And if we load just this first item of the list, then to load the second item, usually your processor, when you go to load something from memory, is going to take a big block at once and stick it in the cache. So if we do that with a linked list, we don't get any advantage from the cache. If our next cell is over here past that, we're going to miss this block of memory in the cache, and we're going to have to go and grab another block, right? And then when we go to get the next item, we're going to miss what's in the cache again. We're going to have to go and get another block. So this is bad locality, and cache access is, 3 orders of magnitude faster than going out to memory. So this really slows you down in practice.
When was this paper written? Because I've heard that, if a linked list survives garbage collection, they'll typically be mostly adjacent depending on your garbage collection.
Right, yeah, depending on the garbage collection strategy. So we'll get into that a little bit later. So the paper's from 2000.
Okay, because he mentions a penny or two, so that gives you 3.
He plays a little bit fast and loose with this because at one point he says, we've got really bad locality in a linked list. And at another point he says, if we use a copying collector on our more advanced data structure that we'll see later, then we can get rid of some of these difficulties with this more advanced data structure that we're going to look at in a few minutes. The copying collector is what you're talking about, right? So say all of this stuff here was garbage. In a copying collector, which we'll talk about a little bit later, this garbage would get factored out. We'd copy all of the useful information down to somewhere else and effectively defragment and compact as we do that. So then our linked list has nice locality, which is what you were saying.
That will happen even if the other stuff
Depending on the GC itself, yeah. If you're
And how many pointers there are from other things in this list as well.
right, yeah. So you might end up in the worst case with a still fractured linked list because you have a pointer to the tail of the list, you have a pointer to the next item, and you have a pointer to the next item, and you're following them in that order with other things in between. So if your copying collector isn't sufficiently smart and you have a pathological worst case condition, you may still end up with a very fractured list after. Does that make sense? Ish? Okay. Cool. Right. Locality. So linked lists are also bad for parallelism. What we would like to do in a perfect world is take a long list of things and divvy out portions of it to different cores or different processors, right? And we'd like to do this in a time that is effectively constant. That would be really nice. In terms of the partitioning and in terms of the rejoining, right? Unfortunately, with a linked list, to partition it, to begin with, we have to traverse the list. Traversing the list is linear time. And to rejoin it, we then have to append these things back together, and that's also linear time. So for parallelism purposes, we can't really just take this list and spin it out to a bunch of different cores with the time performance that we would like to have. Does that make sense? Okay, and one more potential problem with linked lists is that I'm only mentioning this because he mentions it in the paper, but they can lead to stack overflows if you're treating them recursively in languages that don't have proper tail calls, which apparently OCaml in 2000 didn't, because he mentions in the paper when he does a performance comparison with OCaml that he could only get up to 4,000 items in the linked list that he was dealing with, and then ran into a stack overflow. All right, I suspect they've changed that since. Has anyone used OCaml recently?
It seems to have proper tail.
It has proper tail calls now.
Yeah.
Oh, that's exciting.
At least,
Or at least it has a larger stack than 40,000. Okay. Right. Cool. Okay, so what is a data structure that can take care of some of these woes for us? Well, it's an array, right? If we have an array, we can take a lot of our cons over here, some of which I didn't write down, but bad locality, stack overflows, bad for parallelism. Mentally include those over here. We can take a lot of those cons and get rid of them if we use an array instead of a list, right? So what are the trade-offs here? If we have an array, you've all memorized this now, right? Yeah, good. I'm trying really hard not to block the board.
You're doing well.
Good. All right, so if we have an array, we have some really nice advantages at our disposal, right? We've got fixed time or constant time access to any element that we choose. That's really nice. We can partition this out nicely to multiple cores. We can put the results back into an array nicely. We have great data locality. So how's an array built? I mean, effectively, we're going to take a big chunk of memory that's all contiguous, and we're just going to grab this chunk, and if the data that we're putting in is, say, 1 byte, then these are going to be 1 byte slots. Okay. And we know that we have n of these. So this is great, right? We've got the constant time access that we wanted. We've got great data locality. We're incredibly space efficient, right? No matter how big we make n, we're really wasting almost no space here. Maybe we have a constant amount of space at the beginning to tell us what the size of this is. and maybe some other metadata here, but this is fixed no matter how large we make n, right? So what's the problem with this? Why can't we just use this instead of a list?
If you need to store more than n.
Yeah, right. It's fixed size, right? We only get these beautiful properties as long as we allocate n cells up front. Why can't we just allocate more after that?
Copy is expensive.
Sorry?
Copying the data is expensive.
Right, so I mean, to back that up one more step, we might not have enough room, right? Something else may have already allocated this space, right? So we want to grow our array, but we're blocked here, and getting these nice properties of the array depend on this being contiguous. Because our random read access to a particular point in here, the direct access, comes from taking a pointer in here and then offsetting that pointer by the item that we want. So if we know that we want item 10 and we have a pointer to the array and we know that it's a 1-byte array, so maybe we have a data type in here that tells us how big these blocks are as part of the metadata, then we're going to take this data type, which is 1 byte in this case, and multiply it by the index that we're looking for, and then add that to the pointer and do some pointer arithmetic, and then voila, we've got, let's call this item 10. Right? So that's constant time no matter how large n is and no matter where you're trying to get to it, but it relies on this being contiguous in memory. Now, being contiguous in memory gives us that property, it gives us great data locality, because when we go to get one item, we're going to grab a whole bunch of them, they're all going to go into the cache, and if we start walking through and traversing these, those are all in the cache. We don't have to go back to main memory to get those. That's great. We love that property. Okay, so arrays are wonderful, but they're fixed size. This is a pain. They also have allocation issues because you might not be able to find space for all the things that you want to fit in here, right? You have to grab all that space up front. If we're going to put 1 million items in, we might not have 1 million contiguous bytes in memory if they're 1-byte items. So what do we do then? Well, we have to kind of defragment. This is a really expensive operation that your operating system probably is going to do for you, or if you're doing your own memory management, then you have to do it, right? You have to do all this defragmenting and compacting in order to be able to fit this in. This is bad. We'd rather avoid that if we could. So let's look at some ways to do that. So we've established the problem. Everyone seems to pretty much understand what we're going to try to do. We're going to try to have something that has all the pluses of a linked list, but some of the pros of an array also, and none of the downsides. So this is an interesting task that we have in front of us. So how do we combine these two, right? There's been some research on this over the years. Going back to the 70s, people came up with this idea called cooter coding. Out of curiosity, does anyone know what car and cooter stand for? Wow, like 5 people, and you didn't even Google it. That's amazing and slightly horrifying because, good. Does anyone want to tell us?
I know car is contents of the addressable register. Is that it? All right. I forget what cooter is.
There's contents of the decorative register.
Yeah, it's almost exactly the same. And these come from like the IBM 704 or something. I only know that because I looked it up right before this talk. It's not the kind of information that I usually carry around in my head. But it's something nice to pull out at parties, I guess. All right, so cooter coding, what does that mean? Essentially, we're going to make a regular linked list. But if we can, we're going to... Okay, so here's our linked list. We'll actually put the proper null byte in the end. And we'll build it up this way instead, so it's 213, or 210 rather. And if we want to add 3, what we can do is say, well, we'd like to add a 3 here, but instead of making a cell to point to this, we're just going to slam the 3 right here if we have enough space. And so what we end up with is things that look like this, which is exactly what we would like to get out of, out of an array combined with a list. We may end up with something that looks like this, though, depending on how memory is distributed. Where we've got these cells still split out from each other, right? But some of them are joined and some of them aren't. And whether they're joined or not depends on the particulars of memory when you're trying to put things in here. So this solves some of our problems, but it turns out that performance-wise, it's actually not very good unless you have specialized hardware that's adapted to doing some of these things for you at the hardware level, because there's some tricky bits that you get into, especially if you start mutating. It gets like removing things from the list gets quite tricky. Yeah. So this was an alternative that was explored in list machines and like hardware-based list systems, Lisp systems rather, and it seemed to work fairly well there. But when it was brought over into software with more traditional hardware, it actually doesn't work very well on a performance level. We could also look at unrolled linked lists, where instead of storing one item per console, we store k items, where k is usually something like 3 to 7 items. Those end up having, what do they end up having? They end up having properties that are close to what we want, but just not quite enough. We still have linear time, wasted space. We still have linear time, random access. So they're better. They definitely lower those constants, but they're not quite good enough. And then there's some others. Okazaki came up with this idea of random access lists that get a lot closer to what we're looking for. So those have log time, average case behavior for random access, which is nice. It's kind of like a skip list also, I think. They're somewhat related. And then Kaplan and Tarjan came up with this recursive slowdown idea that seems really interesting, but I actually don't know very much about it, so you'll have to look that up on your own homework. All right, so now that we've kind of painted the picture and set up everything we need to be able to look at what Phil Bagwell actually did, we're going to take a slight break and look at asymptotic computational complexity instead. So another quick show of hands, raise your hand if you already know everything I'm about to say. Okay, so some people are confident enough to raise their hands. That's good. Yeah, so we'll just go through this quickly. You have time and space complexity, and we can talk about either. If we talk about one without really telling, if somebody's talking about complexity and they haven't told you which they're talking about, which one are they usually talking about? Time. Usually time. We have worst, average, or best case properties that we can talk about. If somebody's talking about this and they haven't told you which one they're talking about, what are they usually talking about? It's usually the worst. We have upper bounds, lower bounds, and tight bounds. So this is the part I was actually asking about earlier, if you guys were familiar with, but I think most of you are. So we've got big O notation, we've got big theta notation, and we've got big omega notation. Which one are we usually talking about if it's not specified? Yeah, we're usually looking for an upper bound. I mean, theta would be ideal if we talked about that instead of big O, because we get tighter bounds out of it. But almost always, if somebody's giving you a big O, they're really probably giving you a big theta, right? Have you noticed the trend here? This is really easy to remember because it's the first one that we're always talking about, right? So there's your mnemonic device. Yeah, so and we've got upper and lowercase letters, big O and little o. What's the difference between those? Yeah, I had to look it up too. Nobody ever talks about little letters. Essentially, it just says that, so for a big letter, you can have a graph that kind of looks like this, and you can have your bounding function look like this. So it's asymptotically an upper bound, but it dips under it at a couple points. So for a big letter, this is fine. For a little letter, it has to be an absolute upper bound at all times. That's the only difference. So we're almost always talking about these big ones because the little ones really only matter in the kind of, well, They matter in a few different ways, right? You might have something that for all reasonable bounds has terrible constants, right? So you are big O of n, but your constants are terrible and you're worse than something that's big O of n squared. And little o tells you about that, but nobody ever uses it. Okay, so he's going to make some claims in the paper. He's going to claim that we get constant time direct access, constant space overhead, constant time list operations, and it's persistent. This is amazing, right? This is like a perfect data structure. If only. Those are not actually the claims that he's going to make, because no one's actually figured out how to do that, because making data structures is fun and easy, but also really complicated, because you're constantly making these horrible trade-offs. So what he's actually going to claim is that we get typically constant time direct access, right? So most of the time, it's constant. We get almost constant space overhead, and we get amortized constant time list operations, with a small amortization factor in the end. Okay, so these are slightly more believable claims, but we don't really get the perfect data structure of our dreams. That remains for one of you to do instead. I had this whole little bit about, oh dear, I'm sure this will resolve itself in a moment. Surely, there we go. I had this whole little bit about how the first edition of this meetup, Papers We Love Toronto #1, was an hour and a half in length, and then Papers We Love Toronto #2 was 2 hours in length. And so we were going to look at the linear time estimates of how long this talk was going to be. So if you plot those linearly, then it's going to be 2.5 hours. If we're polynomial, then maybe it's 2 hours and 50 minutes or something. And if it's exponential, then you guys are in big trouble. I'm going to try to keep it to an hour. I think we're good on that, maybe, assuming we started 15 minutes ago. That's right. All right. So here's the idea behind a vlist. What if instead of taking something like, okay, I don't have this on the board. Instead of taking something like an unrolled linked list where we've got, wow, that's horrible, where we've got structures that expand the number of data slots, but expand them in a constant way. So this is an unrolled linked list with 3 data spots. I'm sorry, Ben, you're right behind this wall and you can't see anything that I'm drawing. So here we've got an unrolled linked list that has room for 3 data spots and then a pointer, and then 3 data spots and then a pointer, right? So what if instead of doing this, we grew these components geometrically? So the first component looked like a regular linked list con cell, and then the next one had 2 cells, and then the next one had 4 cells. And the next one had 8 cells, and so on. I'm going to let you mull over that for a moment while I drink some water and erase the board. What happens to our properties and guarantees when we do that? And in particular, how do we do that in a way that's persistent? Right. So let's look at a very awful idea, right? We could, if we wanted to maintain our persistence, we could copy everything. So we could start with a list that has 0 in it and decide that we want to add 1, so we just copy that whole thing, add 1 to it, right? And then we decide that we want to add something else, so we copy it, we make something with 4 slots, and now we've got 0, 1, 2, And we've got an open slot down here. So this is bad because we're wasting tons of space. But as we keep growing, we might have something that has thousands of slots here, and we basically have all of our constant time access properties because we're just making a new array, right? But we've also lost persistence. So we've got horrible spatial properties because we're copying all the time, and we've lost persistence. This is really awful. Can we make it better? So maybe we can find a way to, so not persistent, horrible space usage. Maybe we can find a way to get our persistence back and not worry about the space usage quite yet. So we will keep copying things like this and have horrible space usage. But maybe if we can get persistence back, then we can figure out how to deal with the space issues after that. So in particular, the problem with persistence is if I have pointer A to this list, and then I have pointer B also to this list, and then I push something on to the B list, now A is affected by that also, right? So I've made a change to B, I can observe that change in A, because A is just kind of pointing to this list in general, and I've lost persistence, which we really don't want to do in a functional programming language. We would very much like changes to B to not affect A, because we want to think of our data as being immutable, because that gives us all kinds of nice properties and guarantees. So what do we do? Well, what if A came with an offset, and B came with an offset? Oops. And when we change B by putting in 3, we change this offset to 4, but we leave A's offset alone. What else do we need to do to make sure that we don't bork this up?
When you copy, you have to update the pointers. When you copy, you have to update some pointers.
When you copy, you have to update some pointers. So we do a copy when we're adding new things to the list and we run out of room. If we're persistent, then we shouldn't have to update old pointers at that point, right? But maybe I'm misunderstanding the question. So one problem we're going to have, this works mostly to get our persistence back. It works for this case where A and B are both pointers to the same list that has a little bit of room left in it, and B has gone ahead and updated. If B then adds another item, then we can change B altogether to be a new pointer, like you said, that now has 0, 1, 2, 3, and 4 in it. A still stays the same. And this has some extra space here, and we'll update this to 5. And change the pointer so it points to this one and not this one anymore. Okay?
So the offset is at the end. Is that what you're saying? Like the offset points to the end of that references list?
Yeah, in this case, think of the offset as just being how many items are in the list from the perspective of A. And any items in the list after that, from the perspective of A, don't matter anymore.
Yeah, they don't, as far as it's concerned, it doesn't exist.
Right.
So it's just really like length.
Yeah, yeah. But on a pointer-specific level, right? It's not the length of this, it's how much of that this is using.
Yeah.
Okay. So what happens if we want to cons or push something onto A? We've already filled its spot, right, with B.
So you have to copy the data.
Yeah, so at this point we're gonna have to make, say we've moved on with, so we're going to have to make a fresh copy for A. So if we stick 88 in here from A's perspective, then A is now pointing to this. Okay. Because we can't overwrite this 3 because B might still be using it. So how do we know that B is using it?
The offset of B.
Right, but then when we go to update A, we'd have to know every other pointer in our whole environment that's using some of that data, right? So what we actually need to do is extend this data structure a little bit and put a metadata block on it the same way that we did with arrays earlier. And the metadata block is going to, excuse me, something like the last used item in this particular list, right? We should probably also, because we don't really know this ahead of time, put our size in here as well. So with these two, then we know how many things this can hold, and we know how many it is currently holding. And A, as part of it, so it's a pointer and an offset, A is a pointer, but also has an offset. And we can check that offset against the last used. And if they're the same as they are in the case of B, when we don't have the 3 here, then we can go ahead and add the 3, assuming that it's less than the size. If it's greater, then we need to copy. When we go to add 88 to A, we'll check its offset against the last used. Last used in this case is going to be 4 if we have 1-based counting for some reason. And we're going to realize that 3 is less than 4, so this slot that we would like to use is already used. Okay, so we've added a little bit of constant space onto this, but it's constant and it's only a little bit, and we've managed to get our persistence back. So this is great, right? Yeah, except we're still doing this full copy every time, and we don't want to do that.
Yeah, so with the full copy case, you end up, like, if B has abandoned that old array, we don't know about that, right? Like, whenever B goes to add a 5th element, it creates a new array, abandons the old one, which clears up that old data, like, effectively, but we don't know about it, so
Right.
we would still end up having to do a full array copy or whatever, right? Because we can't trust that.
For A.
For A.
Yeah, that's right. Unless our garbage collector is really smart and has run in the meantime. So hopefully we can do better than this. I didn't actually ask you these questions, and now I've given you the answers, but we've essentially done the hard one, right? So the car, which is just peak, is just follow this pointer and the offset, and you get constant time access, right? Pointer plus offset, constant time, random access into this list. That's great. Coder is just decrementing the offset, and if the offset is 0, then you're done, right? Because we've got fixed size lists that hold, or fixed size arrays essentially that are holding our list. So if the offset is 0 in this case, then we have nothing else, we can't decrement it.
You've done growing geometrically here. Is there some sort of tricky power of 2 reason for that? Or is it just like, let's make it geometric?
There is a tricky power of 2 reason. It doesn't have to be a power of 2, but you get nice properties if you grow geometrically, not in the bad list version, but in the actual vlist version that we're going to see in a moment. This is just kind of to, this part that I'm showing you right now isn't in the paper, but it's my kind of back story creation of how he arrived at this, right? So I'm trying to kind of take you along and give you a motivation for what we have to do to make a vlist that doesn't waste all of our space. And we're almost there. So yeah, car and coder are quite simple. We just move the offset up and down to see the appropriate thing. And cons we've looked at. Cons is the tricky one here. So we can do better than this, right? We can reuse old data instead of having to copy every time. And we have almost everything that we need to do that. We've already got our block of metadata on there. All we need to do is, in addition to size and last used, when we make our metadata block, I'm going to put it at the tail instead of the top now. we've got size, we've got last used, and we've got two other things. We do exactly this idea. We have a pointer to the base or the previous version, and we have an offset into the previous version. So now we're using this pointer and offset idea to add a little bit of metadata to the new block that we create that allows us to say, oh, actually, oops, I chopped it wrong. Oh, actually, the 0, 1, 2, 3 part are over here in this previous array. So we don't have to copy those now. We can point B here, and B can have its own offset into this new branch that's going to have 4, 5, and 6 so far. And then if C is pointing here, and C has its own offset, it might push this further. Our last used increases, C's offset increases, and now B has to do its copy operation the way A did to get itself a new fixed size array if it goes to push a new item on here as well. Okay. Right, so we actually already included last used, and we included size. That was nice of us. And here's what this looks like from the paper. So we can see we have two pointers into this data structure, and they're sharing the 3, 4, 5 at the end, as well as the 6 from this column here. This pointer, so we'll call this one B, has added 7 and 8 to the list after this one started pointing into 6. We then want to add 9 to this one, so we create a new block for it. Alternately, you could think of them as starting from the same list here, and this pointer as having popped off the 7 and the 8, and now it's adding 9 onto it. So we've got our base, our offset, our size, and our last used. We've got a fixed metadata chunk on top of each of these, and then we've got the data underneath that. We're starting over with our new one at size 1, instead of continuing and going up to size 8.
So the base and offset that are on the far left there in the diagram, that ends up being a list of 3, 4, 5, 6, 9. Is that right? Okay.
Or, right, reading from the tail to the head. Yeah.
Oh.
So the actual list reading from the head backward, if we were going to read this list or traverse it, we would start with the base offset pointer on the very far left. We would read 9.
Okay.
And then we would follow the base offset of that metadata block.
Okay. So would it go? Would it go 9, 6, 5, 4 or 4, 5 then?
9, 6, 5, 4, 3.
Okay.
I hope.
Okay.
Does that look right? So that base offset pointer on the far left, we'll call that A. The base is going to point into the base metadata, right? So the offset is here, but really the base is pointing to up there. And then we know that we've got 4, let's call them 4 bytes. We've got 4 bytes that we're using. They're not really bytes, let's call them words. We've got 4 words that we're using, and then we start our data, and our offset is going to be 1, because we're pointing to the first data item, or 0 if you prefer.
So is this diagram conflating or list pointers? Okay, so on the board there you had AG, right? You said that when we modify E because we want this to be equal from A's perspective, but persistent, I don't know if that's quite the same thing as context.
They're close enough, yeah.
Yeah, because we want it to be persistent, we just changed the offset and sneakily stuck it in where we had space. If we don't have space, we want this like extra allocation to add, we don't have stuff.
That's right.
The part's confusing with this diagram is that each
Yes. Yeah, so we ended up doing that here with the base and the offset at the very end of looking at this. That's what gives us our persistence back. And also allows us to share the tail. Right? So if we want both persistence and shared data instead of doing this full copy, so let me back up a little bit more. Ignore this. The full copy version with just size and last used gives us persistence, but we're wasting tons of data because we do a full copy every time we need to allocate more space. If we want to share tails, like we are here, and we want persistence, then each of the new blocks that we allocate needs its own offset into the previous list, because that offset may be different than some other pointer into that list. In particular, in the case on the board, we see that there are two different offsets, right? So if this pointer, let's call this A, hadn't added 9, it would be pointing to 6, and this one would be pointing to 8. If we add 9 and we want to reuse this, we can't just point here, because if we just point there, then we're not going to know that the list should go 9, 6, 5, 4, 3. We would think instead, if we just pointed without the offset, that the list should go 9, 8, 7, 6, 5, 4, 3.
So in my own terms, whenever we decide to insert 9, the version as a whole, the list that we're looking at, read 6, 5, 4, 3, or so. Yeah, I just want to insert 9.
That's one way to think of it. Another way to think of it, so one way to think of it is that A and B were once the same, and then B added 2 items,
Yes.
and then A decided to add an item. Another way is that A and B were both the same, pointing to 8. A popped 2 items off, now it's pointing at 6, now it adds 9.
How did you determine that the last block with 9 in it should be size 11?
Yeah, it's a good question. I think that's just purely a pragmatic decision on Phil Bagwell's part to not double the size if you're creating a new list that isn't where the list that you would have added to is not maxed out. So it's a good question. The question, I guess, for the video is why is the new list that we've added size 1 instead of size 8? Because it would be size 8 if our B pointer that's pointing to 8 added a 9 and a 10. Then that 10 would be the first item in a size 8 array, right? But when we start a new array, because our last offset and our offset are not equal, so we have to start a new array to retain persistence, we start over at size 1. I don't know the entire rationale for this, but this also isn't quite the finished structure yet. We're getting almost there. And this part is in the paper he describes this, but he's going to do one better than this in a minute. And I don't know what he does about the restarting in the one better. I think it still restarts fairly small, but there's some modifications to make it a little bit better. Yeah. Sorry?
What do you still matter?
Well, so one area that it does matter, actually, let's hold on to that question for a minute. It turns out that the answer to this question does matter, but we don't have all the facts yet. Okay. Any other questions?
So one thing that I was confused with was like so on this last used, it's just if we were to think of it, it's a pointer to the address of the last cell it was written to, and then I compare my offset, and if they aren't the same, I know that the list has been modified.
That's right. Yeah. So it's
the diagram is confusing.
it is. Yeah. So last used is always going to be the last number in these diagrams, not including the blanks. Right? There's a blank under 8. So last used is the last bit of data that has been written. And what we would like to do is write the piece of data after that. But if our offset and last used are not equal, then we know that something else has slipped in there and added more things ahead of us. If last used and size are equal, then we know that we're done and we need to allocate a new block. Does that make sense? I found that a little hard to parse also. Okay, so this is a lot better. What are the problems with this? What's the really big glaring problem? Well, one really big glaring problem is that we can't just use a pointer into this. We have to use a pointer and an offset. And that's probably going to kill our performance, right? It makes all kinds of things a lot more painful if every time we want to reference any item in this list, we have to use a pointer and an offset to do it. So maybe we can do better. Complicated reference, yes, thank you. So how do we use a single pointer to do this? So this is where he starts to get into the really kind of tricky tricks, right? There's kind of a single central idea to this data structure, the vlist, which is really nice and clean. It's, can we take, you know, a linked list and the advantages that it has and the simplicity that it has, and give it some of the benefits of an array, of a fixed size array? And the answer is yes, we can, but to do it in a way that's performant, we have to get into some really nasty, like, bitwise tricks here, right? And this is a consistent theme in essentially all the data structures that Phil Bagwell ends up building. There's a nice central unifying theme and like a hard concrete problem that he's trying to solve. And then underneath that theme, to actually make it work in a pragmatic way, you need some interesting tricks. So yeah, so one, I guess I've given away the answer. So how do we use a single pointer instead of using this offset here? Well, one thing that we might be able to take advantage of is the fact that in memory, if we consider this the memory of the machine, these are addressed, right? So every one of these memory cells is addressed. They're addressed in binary. And if we take some chunk of memory and we align the top of that to be at one of these binary counting boundaries, right? So let's just count in binary. We've got 1, we've got 1, 0, we've got 1, 1, and so on. And eventually we're going to get to 1 followed by a whole bunch of zeros, right? And then we're going to get to 1, 0 followed by a whole bunch of zeros, and then we're going to get to 1, 1 followed by a whole bunch of zeros. If we say, you know, we want 8 zeros here or 4 zeros or something, right? And then we make sure that our pointers are aligned so that we've always got those zeros at the end, then maybe we can stuff a little bit of additional information into the pointer in these least significant bits that we're not using. Aha.
So is this why that they're powers of 2? It's because you can make the addressable parts stick into those zeros with ever increasing pointer sizes?
It's a nice idea, but no. But remind me before the end of the talk about the powers of 2 thing, because I want to answer your question, I just can't do it quite yet. Keep bringing it up. No, it turns out that we don't need to increase by powers of 2 to get this, because this is, if we want a constant number of zeros here, then the space that this takes up is a constant size. So each of these blocks that always have zeros, trailing zeros, say 6 trailing zeros, is going to be a constant size, right? The space to get to the next block that has 6 trailing zeros is always fixed. Does that work for everyone? Okay. So if we agree that all of our pointers, like A with an offset of 3, if we agree that A and B are always going to have trailing zeros, then we can use, if we agree that the structures that A and B are pointing into always have trailing zeros, then we can use those trailing zeros to give ourselves our offset that we want.
So does that imply that there's like a max size for these blocks?
It would, yeah. So what we're going to do, so the question was, does that imply that there's a max size for the blocks? And the answer is yes. So what we're going to do is have sub-blocks. And these pointers are actually going to point into a sub-block. A sub-block is going to have a fixed amount of data in it that's determined exactly by the space between something with some zeros at the end and the next thing with that same number of zeros at the end, right? So if we've got 4 zeros, then we've got, what, 16 things in here? Is that about right? Something like that. Okay. And this, we're going to call this a sub-block. And this sub-block is going to have a little bit of space taken up with some metadata. That metadata is going to tell us information about the entire block that the sub-block finds itself in. So then our pointer A is going to point into the subblock. That's not quite right. Our pointer A is going to point to a particular piece of data in this subblock. If we mask out the last, let's say, 4 digits of that with zeros, that's going to point lower in memory. So I've drawn this as counting this way, but really we're counting this way. It's going to point lower in memory to the subblock header, and that subblock header then has a pointer to the data structure's header as a whole.
Okay, so if these numbers with trailing zeros are the pointers, yeah.
They're not actually, okay.
Oh,
so
they're the
I said that
numbers.
wrong.
Okay, they are the values at the.
At every trailing zero location in the block, we have a subblock header. So A itself is going to point to a piece of data. But if we mask out the last bits of A, we're going to land on a subblock header.
The last bits of the data that it points to?
Yeah.
The last bits of the pointer?
Of the pointer A.
Okay, so that's, yeah, so if you're masking out those bits of the pointer, it's the pointer that has the trailing zeros, or?
The pointer, okay, so let's put some concrete values on here. Yes.
So what's happening is, so if I have memory pointed to whatever, I'm not gonna think about it. Let's just say I'm pointing a memory here. I have those last 4 bits. I'm gonna encode that data whenever I go to address it. The data's changed, but those are actually the way I'm pointing to the memory gets messed up a bit. So my pointer will be, let's say it's whatever 1111. I mask that to 0, which tells me where the actual memory address is, and then I can use that last information to get to the end, right? Is that how it works? That's how I'm understanding it.
Okay.
I don't know. So
I didn't completely follow you at the end.
yeah, it's okay.
I'll try doing this again, and then
Okay.
if I've answered your question, don't let me know. But if I haven't, do let me know. All right. So what we want to do is take a pointer. Let's say we have 4-bit pointers, and we would like to shove some additional information in here, right? So we want a pointer and an offset merged together, and here's how we're going to do that. We're going to start with a pointer 1101. We're going to say this points to some data. This points to a piece of data. It's part of a big block of data. That block of data has a header, because as we've seen, we need headers in our blocks to be able to help us figure out what's going on. In particular, back here with another list that this is duplicating some data of, right? Okay. So, as was pointed out earlier, if we mask off some bits at the end of A, we get this, and the number of data items in here is fixed. So in particular, it's 4. And we've got, okay. Let's say there's some stuff in here. This is more data. We've got a ... And then we've got one data item. We've got the data item that we're pointing to, where this list actually starts. This is the head of the list. We've got one more data item, which is going to be at 11. And this is at 1100. Sorry, this is at 1111. We're going to count up. This is at 1101, and this is at, jeez. Apparently I can't count in binary and draw on the board at the same time. This is at 1110, and then we have our header here at 1100. So this is a subblock header. Let's make sure that we're pointing things correctly. So A points to this data item at 1101. So when we follow A, we immediately get the data that we're interested in. Okay, so what do we do if we want to start traversing backwards from A, right? Well, we know that we can increment this and go up to 1110 and look at a data item here. And of course, whether we're incrementing or decrementing to go back depends on how your memory is mapped, but we're just going to fix it and go with it. We can go back one more, but after that we don't know what happens up here, right? We might be at the top where this is the header, and we're going to start decrement or incrementing and thinking that we're getting data, but we're getting into the block header, and we don't want to do that. So before we do that, we're going to mask out these last bits of the pointer. And when we do that, we have exactly 1101, and now we have a pointer to the subhead block, and the subhead block is going to have a pointer up to the actual block. So this is how we managed to pack in an offset and a pointer into just a pointer.
So it seems like in the way we did it before, we had a base pointer and an offset pointer.
That's right.
So every time you're doing this copy, you have 2 pointers. Now we have 1 pointer, but there's all these subhead blocks. That's like every 4 items in your list, you have to like store some metadata. Is that it doesn't intuitively seem to me that that's more performant?
From some perspectives, it's not more performant. From some perspectives, this is more performant than what I'm describing right now, because this has a, in the best case, this has a log n wasted space, right? And what I'm describing, we get back to constant wasted space, because we've got all these subblock headers that happen every k items, where k is proportional to the number of bits that we're masking, right? So from a space perspective, we've lost a little bit of space here, but we gain the fact that we don't have to keep track of both a base pointer and an offset and pass those around through hardware systems that are not designed to handle base pointers and offsets. They're designed to handle pointers. So we're trading a little bit of space here for a little bit of time and convenience, because most systems aren't designed to handle this pointer plus offset idea very well. And this is where we get into the fiddly bits of this data structure stuff. We'd really like to have it all. Nobody's found a way to have it all, so instead we have to just keep going up the hill and making these hard trade-offs and trying to find the best way. Good question. Okay, so in some ways this is really nice because we've got log n space usage. I meant to mention this earlier. Constant and log n are much, much, much more similar than constant and linear, or log n and linear. So when you hear log n, don't picture it as constant time, log n time, linear time, or O n time, n log n time, and then n squared time, all as being equidistant, because those log n's are super close to the constant. So here we don't have constant space, but we're pretty close to it. Here we go back to having linear space. So let's see what this looks like. What did I miss? Yeah, okay. So this is what that actually looks like. Here's one of these subblocks that I've described. And here we're using 2 bits to mask out. So here's our plist pointer. We're pointing to a piece of data. We can mask those bits out and drop down here to our subheader. That subheader is going to contain a link to the index. So every one of these subheaders points up to the index, which then has the same type of pointer to a previous list over here.
So the subblock headers, can those be farther away? So like say you're masking 3 digits.
You could mask 3 bits or 10 bits or whatever you wanted, yeah. For this example, he's doing 2 bits. I think in the actual implementation that he tested, I think it was 4. Yeah, so I think we're using 4 bytes here. This is actually masking 4 bits, and these data blocks are 4 bytes each. Yeah. And this takes up 4 bytes. Is that true? Yeah. Yeah. So we have our data type in here again, like we saw with the fixed size arrays as part of this header, so that we know how large the data is when we go to start looking through it and collecting it back out. And we've got some stuff up in the block header for making garbage collection easier. So we can have log n garbage collection time instead of n garbage collection time. With a typical linked list, you have to walk the entire list and mark it, and that gives you linear garbage collection time performance for the live objects that you're keeping. But in this case, because we're doubling every time, so this gets to your question about why a power of 2, we have log n based to garbage collection performance. Because we're only walking walking essentially these header blocks and marking them. Does that make sense? We have to do a little finagling because the header block actually points here, and then we have to skip down here to get our index pointer, and then we can jump back up to the index and see our previous pointer and the actual block head, and then mark it. Okay, so the other answer to the power of 2 question, why power of 2? One is to get this log and performance for things like garbage collection. But another is to get log and performance for traversing, for random access into the list. So the reason, I said that wrong. We get log in garbage collection performance here. We actually get constant time, expected constant time, random access. So worst case log in, but expected constant. And we get that because we expect that if we're going to access something randomly in here, half the time it's here in this first list, and we don't have to do anything at all, right? And then a quarter of the time it's in the second list, and we have to do a pointer jump to get to it. And then an eighth of the time it's in the third list, and so on and so forth. And if you add all of these up, of course you get a constant. But if we weren't doing this geometrically, then we wouldn't have that typical constant time random access behavior, which I think is one of the things that he really wanted, because it's a pretty major claim to be able to say that you almost always have constant time random access into effectively a linked list. That changes things, right? It makes them, in particular, the first part of the paper talks about using linked lists, but also needing to use special structures for strings and arrays, because you want to get the properties that they have, but they add complexity, they add additional operators that you may not be interested in, they muddy up your language space. So if you could just use this instead, that actually makes your life a lot simpler. And this is a lesson that Ray Hickey learned and then applied in Clojure, where there's not this exact data structure, but something very similar that Phil Bagwell also worked on under the hood. Cool. Okay, does that kind of make sense? To answer your previous question, Ben, the first item here, data, previous, and then a few kind of flags and pointers, is size 2. So 2 data items instead of 1 data item. And the reason is that there are certain kind of worst cases where this effectively degenerates into a linked list. So one of those cases we kind of saw over here on the board before, where we want to add a new item but something else has already added it. You could certainly construct a fairly pathological example where you keep wanting to add items but something else has already beat you to the punch, and then your particular list ends up being just a linked list, more or less. If we were doubling the size every time of our application as we do that, then we end up with tons of wasted space that we can't reclaim, right? Because I go to add a new item, one of you has already beaten me to it and added an item on that list. So I allocate something new and add the new item there, and then later on I come back and I want to add another new item to it, but one of you has beaten me to it again, added a new item. So now I have to allocate a new list, and if I double in size each time, this quickly becomes very space inefficient. So what we do instead is every time we want to allocate a new list or start a list to begin with, we allocate 2 data items, a very simple previous link to handle the case that I was just talking about. The previous link would be null in this case because we're starting a list here. And then just kind of the bare minimum of header bits. And what this ends up doing is giving us space performance that is equivalent to a linked list in the degenerate case, because we've got 2 data items and 2 blocks of, or 2, let's say, words of wasted space. Does that make sense? So we just talked about small lists and the high overhead, and right. So this is great. This is really good. We've got it down to a single pointer. It's persistent. We've got great locality, which I didn't talk about, but for any larger lists, you're going to have long arrays. As you load items into memory, you're going to load a whole bunch more into the cache, and so as you work your way backwards through it, you're going to have really good spatial locality there. and good access time. What's the downside of this? Do I have that on the next slide? I don't. So one downside of this is we keep building increasingly larger arrays. So we end up ultimately having a lot of the same problems that fixed size arrays have in terms of their memory allocation performance, right? If we want to allocate a few hundred K, we might not be able to find that in contiguous memory. And to get these properties, we have to have contiguous memory. So then we have to defrag, right? And then we've also got potentially some garbage collection issues. But we're going to take a quick break and come back to those in a minute. This is VISP. So as part of building this data structure and figuring out how to tune it and how to actually work with it and deciding whether or not it actually worked, Bagwell went ahead and built a Lisp that uses this. So here's some code in OCaml and some code in VISP, the Lisp that uses this vlist as its underlying linked list implementation. And now that you've had a moment to read through that, I mean, the Lisp looks like pretty much regular common Lisp because that's what he based this on. So here's the actual time comparison. A couple of interesting things. One, length in this, we haven't talked about it, but it's log n, of course, because you just, given any pointer, you jump up to the header of that block, and then you walk the blocks, and that's log n. So length is blazingly fast, whereas length in OCaml is, of course, walking the entire list, so it's proportional. You can see the 40,000 number coming in up there. He wanted to do 1 million, but ran into these stack overflows in OCaml, traversing their linked lists in a recursive fashion. I believe he's using 2 different underlying data structures there. I also don't remember exactly what those mean, and they might not be super clearly spelled out in the paper.
So some dash you don't really know, at least.
Well, he's comparing a linked list, but I think it's 2 different linked list implementations, but it might be 2 different OCaml implementations. I'm not entirely sure. Considering that he walked into Erduski's office, obviously he has a lot of OCaml support here. So I think that's part of the reason that he chose it was because of those conversations with Erduski. This was in the kind of pre-Scala-ish days. Yeah, so we've got good behavior almost everywhere. He explains this calculation. The majority of the time here is being taken up, and also potentially in Fib is being taken up with function calls in his Lisp implementation, and also in runtime type checking. So in OCaml, you have cheaper function calls because they're not dynamic. It's all compiled down, and you don't have any runtime type checking because, again, it's a statically typed language and everything's compiled down. So he's getting burnt here mostly just because of the function calls and the type checking, or that was the claim in the paper. Okay.
Just to clarify,
Yeah.
he mentions that both native and light optimizing compilers, so that's probably what the
2 different compilers there?
Yeah.
Yeah, that could be. Yeah, their performance is pretty similar except the slow Fibonacci and the calculations. So, yeah, some type of calculation optimization in the compiler would definitely explain that. Sorry? Where is the table? What is the table?
What is this table?
Right, so what he wanted to do is create a programming language to use the data structure as its fundamental, to use the vlist data structure as its fundamental implementation data structure. Obviously a linked list is intimately tied to the history of Lisp, so he chose to implement something somewhat like common Lisp. And then he wanted to compare it to linked lists in a mature language. So the table is just benchmarks. That's really all we're seeing here.
Is this milliseconds?
Yeah, we've got milliseconds. So, I mean, it's almost impossible to draw much in the way of real conclusions. To say that VISP is 4 times faster than OCaml is a little silly. but we can immediately see that a real pragmatic, actual built version of the data structure that we've just described can actually run quickly, which is a nice thing to have in your paper describing a really abstract data structure, because essentially, otherwise you have no idea how this runs, right? If you don't profile it, there's just so much complexity in the underlying hardware that you don't know what the runtimes are actually going to look like until you actually run it and start tuning it for the cache summons. Okay. So garbage collection is nice. We've got login time for this vlist that we've described. There is some wasted space because, so the wasted space here refers to the fact that when you go to garbage collect, it can be hard to, let me just draw this real quick. So we might want to garbage collect our list. We might have a pointer pointing to here very early in the list that then uses some other list as its tail. But all of this data could be reclaimed because nothing is pointing to it, and we can't reclaim it, right? Unless we teach our garbage collector how to truncate things, how to truncate these when there are items that are unused. So we'd have to do quite a bit of work to do that.
But
this,
how do you know that it won't ever be used? Like,
well, you don't know that it won't ever be used, but you could walk all the live objects and teach your garbage collector to understand that this space isn't used by any object that's currently reachable.
So what it could do,
but it, like it's, all of them are start out that way, right?
Start off,
Empty until you fill them, right?
yeah.
So, so wouldn't you be truncating a lot and then shooting yourself in the foot because you actually wanted to?
Right, if you're truncating empty ones, you almost certainly would be doing that. If the only active pointer into here has moved on and is now filling up some other data block,
yeah, right, okay.
and this was all full, or at least the first few bits were full, so it had to make its new block, and now those pointers have died, so there's nothing in there,
Right.
then you could potentially truncate. Or, you know, you could, I mean, you could also get really fancy and teach your garbage collector to take this data and copy it over there and get rid of this one altogether or something, right? And you end up fragmenting memory pretty hard as you delete these big blocks, right? These potentially get really big, but you also potentially have lots of small ones. So you could alleviate that pressure with the copying garbage collector instead. So this is a little bit wiggly because earlier I think there was a downside to something that we could have alleviated with the copying collector, and now we are alleviating this. But essentially, you know, this isn't perfect yet. So we're going to introduce an n-dimensional vlist. I know this is what you were all waiting for. And I think we're running slightly low on time, so okay, I'll go a little bit more quickly here. We've got the basics, like you now understand the idea behind this data structure, where it came from, how it can be used.
It's been an hour and a half just to
Okay,
let you know.
so half an hour, and that will put us in the linear slot, and the next one after will be, oh wait, an hour, I have to fill an hour more to make
No,
it
you
to 2.5 hours.
don't have to do anything.
All right, 5 more minutes. Ready? Go. N-dimensional vlist. Yeah, so what we're going to do I have a picture somewhere? Okay. We'll just jump straight to the picture. What we're going to do is, instead of continuing to allocate increasingly large blocks, like 2 to the n blocks, at some point s, we're going to stop. We're going to say, these blocks are large enough. We're going to drop a block in the beginning, and then it's going to have s squared blocks here. So we lose some things by doing this. We lose our constant time random access, and it becomes more like a low constant factor log random access. Is that true? I don't think that's quite true. we still have our constant time random access in this n-dimensional version, because most of the time what you're looking for is going to be in this s squared in one of these, and we still only have to do 2 hops essentially to get there. We gain much nicer garbage collection properties. We gain much nicer allocation properties, so we more rarely have to do a full defrag to fit one of these in, because we're not trying to load in these huge blocks. So we still have our expected time, random access, and our more or less linear wasted space with much less than a linked list. And it hurts our GC times a little because we have to go through and collect all of these individual s squared blocks, right? But it's still a couple orders of magnitude faster than a linked list. So that's it, kind of. So one question, keep in your head this n-dimensional list. This is a 2-dimensional list. You could also have a 3-dimensional list where the next layer above this is s cubed. In other words, s squared of these s squareds, which then result in s's, right? The paper goes on to, or at least this version of the paper, this really early draft version, this tech report, goes on to talk about using this as a hash table, using it as an array, thread safety, and Deques concatenation. All of those in some ways have been supplanted by subsequent research by Phil Bagwell and others in these areas. So I want to just give you some kind of teasers as to what those end up becoming over the next decade after this is written. And if you're interested, you can go out and read these papers. There's not only really interesting stuff here, but stuff that is very actively used. So vhashes and varrays, these essentially end up turning into this idea behind ideal hash trees, which then ultimately ends up turning into hash array map tries, which are the basis of Clojure's data structure and a lot of Scala's data structures, and Sharp and Haskell as well. We're actually, this Friday, 2 days from now, going to be reading ideal hash trees at the local chapter of the Computer Science Cabal. So if you're interested in that, you're welcome to come out and read that with us. But you can start to see how if we take this n-dimensional idea, or this particular array idea, and push it to the limits and have kind of a tree of things instead of this list of arrays, then maybe we can get a lot of the performance that we're looking for, and also a lot of the space utilization that we're looking for by going for a full tree instead of a list of arrays. And that's the direction that this idea starts to pursue, and we end up with things like hash array map tries. Really, really interesting stuff, and incredibly useful in modern functional languages. He mentioned thread safety. There's a section on it in the chapter, and the section basically says, add a thread lock to the top of your block, and then twiddle that when you're writing something. So what you'd really like, actually, is a lock-free concurrent data structure that does most of the rest of what this data structure does in terms of its properties, and in fact, C tries give you more or less exactly that. So this is another paper by Bagwell with, I think, Odersky and Prokopek and some other people. So this is in active development now, this C tries. They're coming into languages now, but this is from 3 years ago, maybe, something like that. They're very recent, very modern. RRB trees are the same. So this is a catenable way of doing things. This isn't quite what he's describing here, but I feel in some ways like, and I don't know for sure, but that his research into this maybe ultimately led to working with Tiak Romp to do RRB trees, which are like C trees, another advanced data structure that's just kind of coming into languages now. This paper came out again, I think maybe 3 years ago, 4 years ago. Very, very interesting stuff. So, data structures. They're fun, they're exciting, and they're puzzling. It's kind of like doing a giant multi-dimensional Sudoku puzzle. that can't really be solved, but you're trying to get as many numbers in as you can. There's a lot of room remaining for improvement. So if this is interesting to you, I would encourage you to look into it more, start building some of these yourself, because you too can be a computer scientist. All right, thank you.
I have a question, so just hold on to the mic. So, about the subblocks again.
Yeah.
So it relies on masking the bits of the pointer to figure out where you basically like chop off the last few bits.
That gives you the subblock
that
header.
gives you the subblock header. So when all this gets laid out for the first time, does it need to, like, once it gets some memory allocated, does it need to then look at the value, like look at the actual pointer to figure out where those subblock headers need to be?
So,
Like,
say that last bit.
Does it need to look at, like, let's say the pointer that it, when it wants to allocate memory for a big block, let's say the pointer it gets is 1101, does it it can't control what pointer, where the memory starts, so it gets some random
Yeah,
pointer.
so it just fills in some noise at the top before it starts the block, so that it's double word aligned at the start of the block. So if you ask for an allocation from your underlying operating system, and it gives you some memory back, there may be a way in your language to ask for double word aligned block, or you can just say, give me a bunch of memory. You ask for a little more than you need, and if you don't get the address that you want at the top, you just fill in a little bit of noise.
Okay.
And then start the block where it actually should start, so everything else is aligned on those word boundaries.
Got it.
I don't know if that's actually how you do it, but you could do it that way.
Right.
Any other questions? Okay. Well, let's eat some more food and drink some more drinks and make merry until they kick us out.
Right. Thanks.
Thank you.